My name's Ash Lyons. Join me as I try and figure out what quantum science is really all about. Welcome to Cracking Quantum. I was trying to think the other day of how long we've known each other, because it's been quite a long time now. Mm-hmm. So I started my PhD in 2013, and I think we knew each other for about a year before then.
Yes, I think so. Because there was undergrad at the same university, and then we knew each other through there. Yeah. And then you started your PhD, and I did some projects together with Daniela at the time.
Yes. Yeah. Exactly. So it must be like it was 2012 then, so 12 and a half
Something
years?
Like that. Something like
close.
That.
Long time.
It's been a wee while.
Yeah.
Jesus Christ.
Time flies so quickly.
It does.
So I'm here with Niclas Westerberg. Nick did his undergraduate degree at Heriot-Watt University, as we were just saying. And that's where we met. Then went on to do PhD University of Edinburgh.
Not quite. So I did my master's over at.
That's right.
So I jumped ship for a little bit, basically, and I went over to University of Edinburgh to do a master's in like high energy physics rather than. So Heriot-Watt does a lot of optics. I don't know what we ended up working on later on, but optics, quantum optics, condensed matter physics, that kind of thing. Whereas here at University of Edinburgh does a lot of high energy physics. So at least on the theory side. So I went over to do a master's there. Then I did go back to Heriot-Watt though for my PhD.
You did, that's right. And then came over to Glasgow. I don't know how many years ago.
It's been a little over 5 years now.
Okay.
Just before the pandemic, essentially.
So everybody started doing everything just before the pandemic.
So December 2019, I came over here again.
That's pretty much when I started teaching as a lecturer, so I had a few months.
Right, of course, yeah, exactly. It was those 4 or 5 months before everything is shut down.
And then it hit right at the end of the semester. I remember the last couple of experimental lab sessions, we just had to shut down completely all of a sudden.
Oh dear, yeah.
But now, so you have a research fellowship with the Royal Commission of 1851.
That one just finished, but yes, otherwise.
Okay.
But yes, I'm a research fellow. But yes, I did have. So this is how I set up my own research through a research fellowship from the Royal Commission for the Exhibition of 1851.
That's right. I always get the name of that wrong.
It's probably and hopefully the longest job title I will ever have, which is that research fellow of many awards. So for a little bit of context, this is money left over from the World Exhibition back in 1851 that Prince Albert and the Victorians organized, Crystal Palace and all these sort of things. They turned out that they went with quite a bit of a profit, and to continue with sort of the spirit. One of the purposes of this exhibition was to promote sciences and engineering in Britain at the time. And the commission was then set up to continue that work, really, to promote it. And hence they've been giving out money to people like myself and others since 1891. And you get a couple of years of doing what basically the heck you want, which is grand.
Yeah, absolutely. And then now the name makes a lot more sense.
Yes, exactly.
I understand what it actually means. So you are very definitely a quantum theorist.
Yes.
In the grand scheme of things, between experimentalists on one side and theorists, you're very much that on the theory side.
Yes, for sure.
So main question I wanted to ask you, what the hell do you do all day? What day to day, what does it actually look like being a theorist?
A lot of coffee, but I think that is something that is universal with all of us in physics.
Anytime I'm out of the lab, I'm just drinking coffee constantly.
Exactly. No, but a lot of these things will be. So some parts, it depends on what I'm working on, but some parts of it will be pen and paper work of literally here. There is, let's say, I have spoken. My type of work. Whilst I'm a theorist, I do want to work with experimentalists. So a lot of these things or projects tend to start with, here's a question that have come up in experiments, or here is something that would be interesting to model. Maybe someone could do an experiment with these sort of things. And it boils down to finding some basic principles of writing down what we call a model. So something, here is the total energy of the system. and then try to, from there, you do some pen and paper work of algebra. Yes, mostly it's algebra from good old school.
Yeah.
And just see where does these assumptions lead to. Typically, you will have to make some approximations because maths is hard, and that is where the trick of being a theoretical physicist is about. Really, it's what kind of approximations can you make to break the least things. So you still wanted to model the world, but you want it like you want to be able to solve stuff.
Yeah.
So they would be reading things you get this starting point and you write out some algebra, see where that goes, trying to understand what on earth does this mean. You can come to some lengthy expression in the end and going, okay, fantastic, what does this mean? And then you try to like prod it in different ways of going, okay, so if I change this parameter, what happens?
That's touched on a really interesting point in the middle of what you're saying there, about the fact that you build a model and this is very much an approximation.
Oh, yes.
Everything that you're doing is never going to be a full description of the world out there. It's only ever going to take certain parts, and it's the parts that you're interested in.
Yes.
But you still at the same time need to make sure that that's matching up to the specific reality, the specific thing that you're looking at as much as possible.
Indeed. This is sort of that's the big part of being a theorist, really, is doing that. It's making informed approximations that is really important.
So does that mean then, because this is probably something that people don't realize all that much, does that mean that the maths can be wrong?
Oh yeah. Or, well, okay, so put this a little bit more accurate. The maths is not necessarily wrong. I mean, you can make mistakes, but it does not necessarily correspond to reality.
Yeah.
Like you can have made sometimes contradictory assumptions, and these can be really hard to spot. You can. So an example. This is something that common. This is something that you mentioned a bit earlier. Is you make something is small, let's say, compared to, and this is also the important part, is compared to, let's say, the wavelength of light.
So by wavelength, we typically think of that also being the color of light that you're looking at, for example.
Exactly. In a meter, how many oscillations do you have of this wave? And also corresponds to color, because that's how we perceive things.
Yeah. But more broadly speaking, you can also think about this as the amount of energy that one photon is carrying.
Exactly.
All of it is basically
exactly. And this is actually what I was coming to there was because you can make this is a very common assumption that you want to make. But then sometimes you would, let's say that you're making this, it's very small, but then you're starting to make approximations to do with the energy scales that are involved in the problem. So say that, the photon energy is this big compared to, like, let's say the energy of this oscillator of some variety. So some funnily enough, a lot of the time when we do the maths for things, we end up modeling things as a pendulum, like the same maths as a pendulum.
Mm-hmm.
So because it ends up describing all things, it has some oscillation frequency, and that's usually enough detail.
Yeah.
And that oscillation frequency has some sort of associated energy with it. And again, that wavelength and that frequency, so then we start to mix those assumptions, but then that length, that's the size of this thing, and that approximation, like that energy scale, they are not completely disconnected from one another.
Yeah.
And that's something that actually you can find this in literature where people have just forgotten about it. They haven't spotted that. That does happen. These things can be really, really subtle. But that's a place where the maths end up wrong in the sense that it doesn't describe physics. It doesn't describe what happens in reality anymore. The algebra is correct, typically. Yeah. It just might not actually describe what happens.
That's a really good point, because this is obviously quite a fundamental assumption that people make. So kind of summarizing what you just said, you've got, let's say we're looking at light, you've got an electric field which is oscillating. And when we talk about wavelength, you say, well, within a certain distance that it's traveled, how many times it's oscillating. And this is equivalent to saying frequency within a given amount of time, how many oscillations there are. And where the speed of light is constant, these two things should be equivalent.
Sure.
But this is already making an assumption, for
Yes.
example, that the speed of light is constant.
Yep.
So most of the time it works out, but what maybe better for me to ask you this, what are the occasions where it doesn't work out?
We should be a little bit careful there, of course, because the speed of light, if we think of it in free space, in vacuum, is of course, it is a constant. However, if you go into some medium, so what we mean is glass, something like that.
Anything, for example, which is transparent,
Exactly.
the light can be traveling through.
Exactly. So it will travel through it, and in that medium, this relationship is no longer. It will travel slower than see the speed of light. So, but that's what we mean by the speed of light in vacuum. What then you can have places where your link between how many oscillations you have in time and how many you have in space can be significantly different compared to the vacuum, right? And this is a case where your approximations might start to break down a little bit, right?
Yeah.
Because let's say that you've made this assumption that your energy is of your oscillator is much smaller than the photon energy or something like that. So that is a statement about frequency, about things in time. Well, let's say that you are in a medium where that light starts to travel really, really, really slowly. Have situations where, all it happens, it's a not very transparent media in a sense. Things where you get a lot of reflections, that's typically where it starts to really slow down.
So just to throw a few numbers out there, so when we're talking about, for example, glass or in water, light will travel about 30% slower than it usually does, something around there.
Yeah.
When you're talking about these kind of media where light travels really slowly, how slow are we talking?
It's usually a factor of 100 or at most. Like this
is a crazy difference, something that we don't see in everyday life.
Exactly.
It's a very special material.
These are special cases, of course, yes. But then all of a sudden you go, oh, okay, but my wavelength now is 100th of what I expected it to be.
Yeah.
And typically when we do these approximations, like just again numbers to it, if you're assuming something to be small compared to the other, up to 10% is probably the maximum size of, let's say, the small object can be up to 10% at most. It's not going to be super accurate at that point. At 1%, it tends to be super accurate. Like this is it's a small change, so you can deal with these things.
Yeah.
But then all of a sudden, if you have this other, if the wavelength all of a sudden became 100th of what it was in free space, well, then your assumptions now you are, well, that object that is 1% of the size of your wavelength, well, 1 over 100, they become the same size.
Yeah.
And that changes things, and then you have to deal with things differently. You have to try other types of approximations that don't make that particular assumption.
So in other words, you need to find, let's say, new equations that kind of fit the situation that you're dealing with. And that's part of the challenge of being a theorist, is matching up. Well, I've got this whole bunch of tools, this bunch of equations and assumptions that I can make. Which ones do I pick that match the situation that I'm looking for and the thing that I'm actually looking for, the effect that I want to see, for example.
Exactly. As you can easily get an answer. This is the same thing as you put things on a computer, and so if you do some sort of simulation, if your code isn't working properly, or if let's say that if you put rubbish in, rubbish comes out. This is
of course. This is like everything.
This is true. This is true also in theoretical physics and things like that. I remember at some point this is a pure theory paper with another colleague, and we got to here's some results. This was about Bose-Einstein condensate. So this is they are fluids made out of atoms. They behave like a big quantum mechanical object. They're a bit weird in essence. But we realized that we were doing something about how the sound waves inside this fluid, how they behaved. And at some point we had to, here's some results. Have written out a paper. So we should publish this. And then we realized at some point that, we had expanded to this order in that equation and another order in another.
Ah, okay.
The next order term ended up canceling what we were looking at. You really have to be consistent with these things. So, okay, well, I guess it's a different story now. We just have to rework it and see what happens.
That's really interesting. It matches up perfectly with what you were saying before about assumptions, because again, slightly rephrasing what you were just saying, you're talking about, let's say you had these two different equations, and one was done to within a higher precision than another one.
Exactly.
And when you looked at the higher precision for the second equation, you just saw that.
Oh, yeah, it was some cool physics coming out that, oh, this is unexpected behavior. That's always, I think, like if you have something that is unexpected, do double check. It's that your gut feeling can. I mean, that is a time when you really should go like, have I done a mistake here? Yeah.
That leads me to a kind of open question I've had in terms of theoretical physics for a while now. So obviously an important part of the scientific process is peer review, meaning we write our papers, we send them out to other scientists who read them and basically say, how important is the claims that we're making? Is everything done correctly?
Are you like consistent? Is this making any sort of sense?
Yeah, exactly. Just to kind of like validate that what we're doing is right. Now, as an experimental physicist, which I am, if I look at another experimental paper, I am not going to go away and redo all of their experiments because it's completely intractable.
Sure, you can't set up another experiment to.
Yeah, if it takes someone 3 years to get their measurements, I'm not going to go away and repeat them to review the paper. Exactly. But I can still.
So I presume you look at the things like, is this plausible?
Exactly.
Are you so compared to these are the you can look at. Presumably, you get things about optics.
Yeah.
So there will be like components in common, many of them. You go, the size of this lens and these distances, does this add up?
Yeah, exactly. You can like broadly check that things make sense. But in terms of the theory side of things, I mean, if you read a theory paper, the framework is there. So do you go through and check through someone else's maths when you're peer reviewing a paper? Or again, do you just kind of like broadly look at it and say, well, this kind of makes sense?
So it depends. Often, no. Often we trust that the algebra is correct. Again, this will be more stringent if there are unexpected results. So things, and again, what do we mean by unexpected? Things that, let's say, break principles that we are. I mean, at some point you can somewhat spot that something must have gone wrong with the algebra because, let's say, you broke the conservation of energy principle. I mean, you can't that sounds like a joke. That happens. I get papers where you go like, okay, what you've done here doesn't, like, you are getting energy out of thin air. And obviously something must have gone wrong, and then you try to pinpoint where did something go wrong. And maybe double check some algebra, and that depends on the claim. What exactly are they claiming here? Are they setting up a particular, let's say, so typically in theory papers you get almost two different kinds. You get the ones that are, here I am going to build this overarching model or technique really that we can apply to many different problems. And then we have the ones that are, here is a particular, we have explored one section of something, or we're trying to explain one experiment or something like that. So much more narrow type of works, and both occurs. Everyone does a bit of everything there. In the bigger framework ones, if you end up with there being claims that look a bit odd, you want to probably double check these things. Otherwise, it's very much like, here you look at, again, is this plausible? Is this result? Does the algebra look like, I'm not going to repeat those steps, but can you kind of guess how you would go from this point to this point in certain steps there?
So you can kind of see what's likely to happen if you follow through the maths. You can spot certain patterns in the way that you analyze things.
So it's amazing how much you essentially becomes a gut feeling, right? It is of you have done these type of calculations so many times and probably done them wrong a few times, and you've just done them and it becomes a part of, oh, this looks odd.
Yeah,
like this step looked odd. What's going on here? So a lot of the time, so this is going back earlier to in our conversation here, is the importance of approximations. What I end up putting more emphasis on when I peer review is, in absence of any obvious algebraic error, and the results look plausible based on these equations or something like that, what are the assumptions they made? And are they compatible with real world? And are they intercompatible with one another?
It all comes down to the assumptions.
Exactly. So, and it goes down to assumption, and it goes to what is the physics of this? Like, why do you have a good physical explanation for, if you see, let's say, there is a particular parameter value where you have either like a strong peak in the amount of photons you get out in this particular example, certain amount of light you produce, or something where it completely dies down, so you don't get any photons out. That typically has some sort of underlying physical explanation for why. And it's asking those questions. Sometimes, if it's a really good paper, people will have thought about that and everything. But so our job as peer reviewers are not necessarily always to go to just double check. It is also there to go, okay, but can you please explain why this is? And I appreciate those comments when I get them as well, because then it means that, I mean, the job of a scientist writing a paper is we need to explain what we're doing and what is going on, right? And if I get confused as a reader, or if another peer review gets confused on what is going on, clearly not on our job, right? So need to explain these things.
That's a good point. Part of your job when you're looking at someone else's work is to really try and assess, are all the explanations actually there? It's not just about presenting the work, presenting the results. It's about their interpretation. It's about how you take that information and you turn it into from maths into words.
Exactly. And of course you have to be careful there, because almost always there are multiple ways of interpret things, and you sometimes have to accept that is not my way of understanding what is going on, because we all have some sort of simplified pictures in our head. But it's an equally valid way of thinking about it. And you just have to catch up from that one. You go, no, this is fine. It's just not the way I understand it, but it is fine.
It's a really good way of thinking about things. I think we all think in models as physicists, so we all have our own independent shorthands for how we describe certain things that go on. But nothing is all-encompassing. Nothing is capturing everything.
No. But also, so in the peer review, it's similar there. It's very much like, no, I am not going to repeat every single step of the algebra. That is unfeasible, because, again, people kind of worked on this for years. And sometimes it can be, here is, let's say, 20 pages of algebra. It really is straightforward, but it is a lot of steps.
That's one of the things that you find. There's a specific type of mathematical notation that we use in quantum physics called Dirac notation, where actually working with the maths is incredibly simple on the face of it. The actual steps and the calculations that you need to do are easy because it's been really, really simplified. But you end up with these huge equations that can take up like entire pages if you're not careful. So in other words, you need it that simple, otherwise it's just completely impossible to
you need to condense things down. You need to write shorthands of, this is what I mean when I write Dirac notation. We often mean like, here is a wave function, here's another wave function, and this is the overlap, or this is an overlap with some sort of function. By overlap, I mean it's you compute the integral of this function times that other function, wave functions. And integral over all space of that. That's what we call overlap. But you're not going to write that out every single time.
No, of course not. 'Cause you turn your like 1 page of maths into 20 pages if you're writing all of this out.
Yeah.
So what distinguishes, let's say, a quantum theorist from other types of theorists within physics and engineering?
That's a good question. So, in some sense, not a lot. It boils down to what is the toolbox that we are most used to working with.
Okay.
So all fields have some. There is some base equations, so something that we always go to. Okay, so I work a lot with light, so I need to know Maxwell's equations. So these are the equations that show how light behaves, or light or electromagnetic waves in general. And I just need to be super familiar with those, and there's certain approximations that you almost always end up doing. If you are working in a lot of the time with optics experiments, you can assume that light is mostly propagating forwards rather than out. Like it's a laser. Think a laser beam. As soon as you have a laser beam, it's mostly like it's not changing so much in size. It's a little bit, but not super much in size. For the length, like over an experiment. And that mathematically boils down to a particular type of approximation called the paraxial approximation. It's an old optics term about angles being small. That's what paraxial mean. The angle of deviation is small.
And of course, you could be making pretty much that same approximation for any kind of wave mechanics that you want, but it's particularly useful when you're dealing with light.
Yeah, exactly, and often the cases that we are looking at. So this would be a horrible approximation if we're talking like let's say a radio antenna. Or acoustics or something that just goes everywhere. Because you are just, it would scatter everywhere and it goes everywhere, and no, then it's a bad approximation. But in this particular case, it's a good one. But what I mean is that this is just a part of the toolbox of, I know that I will probably have to do this. And at some point you should just go on, or my starting point might even be, here is that approximation. And I know how that couples into, if I have an atom there, with quantum mechanics, or also if you're dealing with the quantum bits of the photon, it's just that the photon still behaves like that wave. So you can continue with that kind of maths. In other fields, you have similar, just ingrained approximations that you almost always do. I used to work a little bit in high energy physics, and one that I find a bit funny, that coming from someone that works nowadays a lot with, in their terminology, low energy physics, because it's not the LHC. It's low energy in comparison. Because at the speeds that is happening in the LHC and things like that, you can almost always just say that all particles don't have a mass. Because of most of the energy that is involved is that kinetic energy of it moving very, very, very quickly. That mass, it's a small correction. You sometimes have to take it into account, but it's a small correction.
So what you're talking about there is I guess, Einstein's famous E equals mc squared. There's a difference between energy and mass. And where we have lower energy particles, that's where most of the energy is in the mass.
If it's moving slowly, well, then the mass is really important because it's like it has a lot of energy. Whereas in high energy physics, you can just throw that away. It's like, to first approximation. Again, this is what is ingrained, and we always do these approximations. And then we should probably look at what happens if we add this back in again. But that is one part of the standard toolbox. And then also how you formulate the maths from the starting point is different. Because again, you use slightly different ways of what's called quantizing. So going from a classical theory to a quantum theory, to something where you have waves, to something where you have particles, in essence.
So when you go from the classical theories to quantum, what's some of the biggest jumps that you see in terms of the overall effect? This is probably a really hard question because it's quite vague.
I guess part of it is in the name. It's quantum, it comes in packets. And somewhere after this, it will show up in packets. But conceptually, of course, what you are dealing with all of a sudden, instead of talking about I have a trajectory of going from this point to another, no matter how you do this, when you're going from a classical to a quantum theory, you are saying that, oh, I know, let's say, the likelihood of me having a particle here and then later on a particle at some other point. You don't know which path it took, you just know that there's a likelihood there, that it's going to show up. You have to go to probabilities. All of these things, it's ingrained in the theory. It's seemingly how, as far as we know, it's how the world seems to behave. Again, is this how the world works? Who knows? But it is a really, really good description.
Yeah, absolutely. And there's a very good example, which is the process of random number generation. So this is important for things like communications and security, among like many other things. You need access to random numbers.
And actual, truly random numbers. Something that is, if you do it on a computer, otherwise you do a random number, well, it's just a really, really complicated algorithm of taking your input number, usually just time or something like that, the CPU time, and throwing out another number. But it's technically predictable.
Yeah, exactly. So you take the example of rolling a dice. If you take the same dice and you roll it in exactly the same way, you could probably get the same number, like really high level of certainty. If you roll a 6 the first time and you do things in exactly the same way again, down to like the air resistance and the friction.
Exactly. You somehow managed to control all of these things.
You would get the same number. But there are processes within quantum mechanics that, as far as we know, are truly inherently random. So if you build a quantum dice, if you want to phrase it that way, you roll a 6 the first time, the next time you do it, you could get something completely different. And it is truly down to just random probability.
That seems to be... So this is, of course, the big conceptual step. Mathematically, it really depends on what maths you are working with, because there are ways of formulating a classical theory in such a way that it's really similar to quantum, how we usually formulate. In fact, this is one of the ways that we formulated quantum mechanics in the first place. The only thing that really changes in your equation is that you put a little hat on it, because that's how we note that, oh, this is not a field anymore. Oh, it's a quantum field. It's now has this inherent randomness to it.
And by hat, you mean like you draw a little arrow. It's not you draw a little fedora or something on the top.
That would be a really good one. But yeah, we call it a hat, but yes, it's a little arrow. And sometimes that is the only real thing that changes. And then, okay, you have to then remember that, oh, if I multiply this field with another, there are some new rules that we have to take into account.
But again, it's all about the interpretation. As in, when you're doing this, you're making an approximation, and you're basically telling anyone who's reading, these are the approximations that I'm making, so they know what steps to follow afterwards. Exactly. It's not just that you turn everything super simple. It's not quite that straightforward.
No. As simple as possible, but not too simple. That's sort of a generic theme. I think it's you want to make your description of the world with as few things as possible as requirements for it.
Exactly. It's Occam's razor, essentially. You can take two different, let's say, descriptions of the world, both equally valid. You take the simpler one.
Sure.
Because you may as well, and it makes life as easy as possible. Occam's razor is usually phrased differently, but that's kind of like
that's the essence of it.
Yeah, exactly.
One of those things in specifically for theory, but this also occurs honestly when you're fitting any sort of model, or if you are doing things, is if you make your equations complicated enough, you can probably explain any result.
Okay.
It just doesn't mean anything. Like the famous one is it's a pure maths thing, right? It's purely, if you have, let's say, 25 data points, you can always make a perfect fit with a 26th order polynomial.
As in, you include enough variables in your equation, and it's always going to fit perfectly.
In between those data points is utter nonsense. But it will fit those exactly. But what it means is that this is something we always have to be wary of in theoretical physics, is that you can make, if you are not careful, you could make things so complicated that you actually are not explaining anything because you are fitting some data, but when you all find it, this predicts, or like in some sense, if you have the data already, you're not predicting anything. You are saying that, it fits this data. I can explain this data. However, then you often run into the issue, but what if we, in the experiment, change a little, tune some knob?
Yeah.
You might have to change your parameters completely, which means that your model is nonsense, right? It has nothing to do with the world. Yes, you explain that data, but nothing else.
Yeah.
So it needs to be simple enough to, and usually the amount of parameters you have in if you only have a few of them that you can change, well, then it also has predictive power then, because then you can say that, for this experiment, I needed these parameters.
What is your favorite random science fact?
I had to think a little bit about this one, but random one also sort of, because again we both work on quantum physics, right? And I think one of the one that I find both weird and funny is that the existence of yogurt it requires quantum mechanics, because if you model all of the, I mean, obviously from the you can go silly, of course, because quantum mechanics don't have atoms or molecules or anything like that. But specifically, the forces that are involved in making these sort of the fats in your yogurt are actually forming this sort of structure that it is not quite liquid; it's somewhere in between. That force can only come about because you have these probabilistic fluctuations. Otherwise, it would all be way too strong, and everything would be cheese, and everything would just clump up.
That
end
is
up in the bottom.
Genuinely really interesting. That's not something that I would have thought. Thank you for your time, Nick.
Thank
Pleasure
you much,
as always.
That was good fun. It was good fun.
Really interesting discussion. Thank you.
Thank you.
You've reached the end of the podcast, which probably means that you enjoyed what you're listening to. So please don't forget to like, follow, subscribe, and share this podcast series as much as you can. The more you do those things, the better this podcast is going to be. Don't forget, you can always contact me by email at ash@crackingquantum.co.uk. And please join me again for another episode of Cracking Quantum.